Welcome back to 8701. So in this section of our discussion of instrumentation, we talk about accelerators. And I'll do this in a little bit of an historic way, showing you some of the developments over the last up to 100 years. We use electromagnetic fields in order to accelerate charged particles. And so the developments in understanding electromagnetism led to then, the technical developments or the technological development of accelerators and the availability of devices which can be used in order to accelerate or modify particles. And so this goes back to Maxwell and Hertz discovering electromagnetic waves towards J.J. Thomson, who was able to use cathode rays and the classical Lorentz force in order to understand electromagnetic fields. If we study particle accelerators, we can see three different historic lines: the direct voltage accelerators, resonant accelerators, and transformer accelerators. And so we go through those three different subjects one by one. The energy limits of our accelerators, they're typically given by the maximum possible voltage available. When you're thinking about accelerators used for colliding beams, it's not just the energy which is a limiting factor, but you also need a sufficient number of particles to be accelerated and brought to collisions, and those particles need to be in some sort of beam which is narrow such that collisions are possible. Requirements change depending on whether or not you have colliding beams or fixed target experiments, whether or not you actually study lepton collisions or hadron collisions, whether or not you're using secondary particles as the means of what you want to learn from this. But the concepts are very comparable across those individual fields of study. So let's start with the Van der Graaf accelerator. So you basically have to be able to create large voltages, and what a Van der Graaf accelerator is doing is creating this large voltage by just moving particles from one level, separating particles to create this large voltage. You can typically get up to megavolts and tens of megavolts of voltages, but you need to make sure that you don't enter a breakdown kind of regime. And so it depends on what kind of insulating materials you use. If you are using insulating gas under certain environmental conditions, you get up to 17.5 megavolts, which then can be used in order to accelerate. You can use the fact that you can use the electric field twice in the tandem accelerators by just changing the direction of the voltage. Large potential differences have been a field of studies in the 1920s and 30s, and one not so, and it's just noteworthy that this is a dangerous field. So Brahe and Lange, they used potential from lightning in the Swiss Alps, but this was fatal for Lange, who was electrocuted fatally by a lightning strike. So then you need to think about how can you make your large voltages available and how can you make them available for acceleration. Cockcroft-Walton accelerators use a sequence of a cascade generator in order to reuse the voltage in order to create a larger potential for acceleration. The Marx generator is conceptually is very, very similar. Those are still used today. So while those developments are 80 or 90 years old, if you go to a Physics Today article from 2003, you see that a machine like this is being used in order to create the initial confinement for fusion reactors, and the total power is rather fascinating. It's 4 terawatts, which can be released in 100 nanoseconds from a larger number of those Marx generators. In modern particle physics accelerators, we use resonant acceleration quite a lot. And the idea is really like it's shown in this picture here, that the charged particles, they're kind of being accelerated on a wave. So basically they're surfing on electromagnetic waves. And this can be seen here. You just place them correctly in your waveform on a specific point, and then they can be accelerated over some distance. So the key point here is that you have a proper or correct phase relation to the accelerating voltage. And the setup can be, varying, and historically there's various attempts to do this in an optimal way. The first one is the cyclotron, which has a static magnetic field, and in each turn, your particles are being injected, and in each turn, your particles getting a kick here and a kick here, and because their velocity is increasing, their radius in a fixed magnetic field is increasing as well. So after some time, the particle is accelerated and leaves the cyclotron with a specific velocity. Focusing here is important. You don't want to just inject particles and then they spray all over the place. And in accelerators, physics and having the right optics for the particle is a key part of the work needed here. There's a number of techniques. I don't want to go into too much detail, but what you typically see is if you compress the beam in one direction, it decompresses in the other direction. And so quadrupole magnets can be used in order to, get some focusing, and you use, fringe fields or edge fields in order to make sure that the beam itself stays in a compact form. You can also, do techniques where, you have this initial focusing in one direction and then in the other direction, so the resulting beam can be made smaller. Accelerators are not just important today in particle physics, but they are specifically found their place in medical applications, in tumor therapy specifically. And the history here is very long. You see those initial ideas or methods where neutrons are used, 10 MeV neutrons are used in order to treat tumors. We haven't discussed this in nuclear physics too much, but when you use ions as a radiation form, you can really pinpoint where energy is deposited. The so-called Bragg peak is used in order to, precisely figure out in a three-dimensional way where the energy of the ions is being deposited. This is in contrast to radiation therapy with photons, where you just basically spray a larger part of the live material and just destroy the cancerous cells, but also the ones which are still healthy. Any given larger hospital nowadays has a small accelerator, and so there's thousands and thousands of those available, and the work and the maintenance of those is rather important. But continuing the discussion of accelerator concepts, this kind of racetrack accelerators are quite interesting. You basically have a couple of fixed nets in your particles being injected, and it's getting, like in the cyclotron, larger and larger kicks, and then at some points can be ejected in order to do experiments. Again, this is not the technology which is not in use anymore. MAMI is an accelerator at the University of Mainz, and it's the next generation is using next generation of accelerators at this facility is using a similar technology. The question is, what kind of conditions you have to fulfill in order to keep the particles in place. And here, because the particle moves along, it in each turn takes more time in order to make one circulation. So what you want to make sure is that your phase and the acceleration stays in sync. So you want to make sure that the particle, when it comes around again, gets another kick and it's not deaccelerated. And so that explains why in those machines the particles are bunched. They come in little blocks of particles instead of just being a continuous stream of particles. And you can work out the conditions necessary in order to fulfill the requirement that particles are being continuously accelerated. So then there's, over the history, a number of technologies which make try to make use of the fact that when you accelerate, the velocity of the particles increases. And so initially, at a specific time, with one sequence, the particle gets a kick, and then in the next time it's already faster. It travels further. So you can, there's literal linear accelerator structures. You just increase the length of each accelerator structure in order to make sure that you again can give particles the necessary kick. Nowadays we use cavities, and we use superconducting cavities in order to make them energy efficient and in order to have large gradients. The general idea is, again, that you place your particle in here and you place it such in your face, in your varying electromagnetic fields, that it always gets a kick instead of being on the other side and being deaccelerated. Again, the Alvarez Linac is a very similar concept. The advantage here is that you only have one power input, which then you couple, and the walls of the machine don't dissipate energy. So then the next, once you have an accelerator structure in place, you also want to make sure that the structure itself doesn't interfere with the beam, that the power transfer is as efficient as possible, such that you can get more for your buck. All right, I mentioned this a few times already. The fact when you have an electromagnetic wave of this form and you put your particle here, the question is, what happens with particles which have a slightly higher energy or with particles which have a slightly lower energy? And it turns out that this kind of wave has a self-focusing kind of structure, in a sense that the particles who are a little bit behind, they get a little bit larger kick. Particles which are a little bit in front, they get a little bit of lower kick, which means overall in energy you focus your bunch. In energy and space you focus your bunch. And you can go one step further using IF quadrupoles. Again, no details given here. You use these units in order to further squeeze the beam and reduce the footprint in energy and space, the phase space your particles are occupying. All right, the next level here is then to use a Betatron, and the idea of the Betatron is that you change the magnetic field as you go. Instead of changing the size of the structure, you change the magnetic field so you can use the same structure in order to confine your beams. And the next level to this is that you just use one magnet, use many magnets, and this is done in synchrotrons, modern synchrotrons. So here, again, a large line in history, but the point is that when you use the same orbit for the particles, the way you accelerate them, your magnet structures can become much, much smaller. So you have many small magnets instead of one large magnet. And only one or a few accelerator sections are needed. So the particle passes by here, it's being accelerated, and then you have magnets across the ring, which are able to change their field strength. Again, if you have constant field strength, the radius changes, but if you're modifying the field strength accordingly to the speed of the particle, you can keep the particles in the same circular structure. More words on the focusing. Again, if you place the magnet such that there's a gradient in the field between, depending on the position, you can use that fact in order to have particles which are further out being bent more inwards, particles which are further inwards bent more outwards. This is called weak focusing. And you can do this not just once, but twice, by changing the rotation, and then that's called strong focusing. Synchrotrons have limitations. There's two which are rather important. The first one, the radius of the synchrotron is determined by the momentum of the particle and your magnetic field. So at some point you run into technical limitations on the magnetic field strength. Modern superconducting magnets, they get up to in the order of 8-9 Tesla. We are able to produce accelerator grade magnets of up to 14 Tesla using superconducting materials. And so that with a fixed size of your tunnel, of your ring, limits the amount of momentum you can give or energy you can give to your particle. And so for the LHC, we accelerate protons up to 70 eV in one beam, and we use a magnetic field of 8.4 Tesla. So that's really the maximum the machine can actually deliver, and we haven't actually demonstrated that we can get up to this point. Right now, the center of mass, the proton energy is 6.5 TeV. The previous concept and construction had started in Texas in the United States in the so-called SSC tunnel, which was much, much larger, required an 87 kilometer tunnel. The idea was to get protons to energies of 20 TeV with magnets of 6.8 Tesla. Okay, this is one limitation, the size of your tunnel. The second one is when you bend a charged particle with a magnetic field, it radiates, and it radiates proportional, the energy proportional, energy over mass to the force power, which means that you at some point are limited by the power you have to invest in the beam to even just keep it at a specific energy. So this is E over M and to the force power. And this also gives you a clue why we actually accelerate protons in the LHC and not electrons. The electron mass is too low, and this goes to the force power here. The synchrotron radiation of electrons in the LHC tunnel is just the limiting factor. At some point, you don't have enough power anymore in order to give that to the electrons or the particles in order to accelerate them. All right, so as I was saying initially, so you need focusing, you need accelerating, and you need, all kinds of additional components to an accelerator in order to make good colliding beams. And so it's much easier to just dump a beam into a fixed target and study what's coming out. So colliding beams as a source for input into particle physics experiments came a little bit later. First concepts came to fruition in Frascati in the 1960s. And then we had SPEAR, a electron-positron collider at center of mass energy of 4 GeV, which then led to the discovery of the JSI. And then later we had a 5 GeV electron-positron collider, which was then designed for 8 GeV. This then continued, as you know, to machines like LEP, which had a center of mass energy of up to 210 GeV, and the LHC, the center of mass energy of design of 14 TeV. So the collider elements, what do you need? You need to inject particles, and so you have to have a source of electrons and a source of positrons. Producing positrons is just, technologically in large numbers much more complicated than electrons. Here you can, just in order to get sufficient electrons, you need to actually produce them with kind of an accelerator structure as well. And so then they need to be focused, they need to be cooled down in order to have them as a beam being injected in the structure. So what you need as additional components, you need your IF generators, you need magnets to bend the beam in and out. You need to have magnets in order to bend the beam around. So we need bending magnets, you need focusing magnets to keep the beam in orbit. And then you want to, before you bring them to the collision, you want to further focus the beam such that you have more actual particle collisions available. And then you have interaction points where you will put your particle physics experiment. What's being done here in this facilities is you inject, you accelerate, and then you store the beam to make sure that you can fully exploit the structure. So those rings are called storage rings. You avoid, having a one kind of shot kind of mentality as you have, for example, in linear machine. Sometimes you do this in separate rings, sometimes you do this in the same ring. That depends on the design of the machine. The challenges are if you have particles travel around for hours, that they shouldn't interact with some gas, for example, in your accelerator structure. You require a very, very good vacuum in order to not lose the beam as you have it stored. The fields of your accelerator structures need to be very stable, and that stable, they have to be stable for many, many hours. That, for example, there's some requirements on your electric grid, for example, such that you have the stability in voltages which don't end up changing the actual field strength of your magnet as you go along. Yeah. So again, I already mentioned this, the further development of those machines. In the 80s at CERN, stochastic cooling was used for the first time in an anti-proton proton machine. And that machine led to the discovery of the W and the Z bosons and first really deeply study of the weak interactions at the scale of the weak interaction. At the Tevatron close to Chicago, protons and antiprotons were brought to collision at the Fermilab, at the Fermi National Accelerator Laboratory. And then LAB started in the late 1980s in the same tunnel as we find today, the LHC. At DAISY in Hamburg, HERA was used to collide electrons with protons, and those results then led to an understanding of the structure of the proton. So you see that the reason why I show you this history here is that the progress we did in particle physics at the energy frontier, each of the energy frontiers, was very much tied to the progress in accelerator structures. And rightfully so, Simon van der Meer received the Nobel Prize in physics as an accelerator physicist for the discovery of the W and Z boson. He was working on the machine and made the machine possible together with Scala-Rovia. An interesting, if you look at the history of those particle accelerators, it's interesting to see how, we moved the energy frontier forward. So what you see in this plot here is the available energy of the machine, and what you see here is the line. And this plot is called a Livingston plot. You see the logarithmic scale, and you saw that for a very long time, there was this logarithmic increase in available energy. So this line is now turning over. We're already in 2020, and we haven't made any progress here. So progress here. There is, however, interesting discussions on going somewhere. I'm going too high. Going somewhere here with the next machine and being able to probe further higher energies. And the way this is proposed for proton-proton collision is by just making a structure similar to the LHC, but with a radius about 4 times larger, about 100 kilometers compared to the 27 kilometers the LHC has today. And so you can compare this with the hadron machines, but also the electron machines, and also on the electron machine slide, this trend is not as pronounced as for the proton machines, but we're basically here, the highest energy electron proton collider is still LAB, which has been decommissioned at the end of the last century. And we are thinking about a next machine. Sometimes you see those acronyms as a linear machine, International Linear Collider, or future circular collider with electron and proton collisions, which would be hosted in the very same tunnel as this machine, which is called FCC PP or HH. HH with 100 kilometer circumference.